our submission for Group 8 Computer-Assisted Robotic Eating Care. Our team consists of 4 computer engineers, Queenly, Shani, Bao, and Twin.
Now let's talk a little bit about the problem we're trying to solve in this project. So for most of us, eating is something we do every day without thinking too much about it. But for people with disability, it could be a real challenge, so many of them have to rely on caregivers for assistance during meals. And because of that, we wanted to develop an affordable and accessible solution that can help these people out. This feeding system can increase the user independence and also the quality of life, while also reducing the workload on caregivers in both home and healthcare settings. Now that we know our motivation, we established a few key goals for our project. We focus on developing an assisted feeding system that is easy to use, reliable, and also capable of accurately acquiring food during each feeding cycle. And to accomplish those goals that we currently have, we also defined some key objectives for the system. These included safe and hands-free operation, accurate food targeting using APRO tags, and reliable control through the food operating buttons. To make sure that our objectives were clearly defined and measurable, we made a set of system specifications to help guiding the design process and also provide benchmarks for evaluating our final system.
This image just shows the overall setup that we have for our robotic feeding system, where the arm will be on the table along with the plate and LCD. And there are foot pedals on the bottom where the user can use those to manipulate the system, whether to start a feed, emergency stop, or selecting food. And then there are also a camera and time of flight sensor attached to the Jetson Orin Nano, which does all the visual computing. Now moving on to our hardware. This hardware block diagram shows the overall system architecture of the care system. As you can see, our design separates perception and motion execution into 2 major parts. The Jetson Orin Nano handles all perception and system coordination, while the MyCobot's internal Raspberry Pi 4 handles all low-level joint control. This separation improves reliability because through the Ethernet, we can make sure that the vision processing doesn't interfere with any type of motor execution. The foot buttons and LCD are also connected to the Jetson so the user can get immediate feedback. For the computational core, we chose a single board computer because it gave us the best balance between processing power and hardware compatibility. Our system needs to run computer vision while also communicating with the sensors, the display, user inputs, and also the robotic arm, so a single board computer would be the most flexible to allow us to do that. For the final computational platform, we selected the Jetson Orin Nano Super because it gives us the processing power for all the real-time vision and object detection that we will be doing. It also easily allows us to integrate our external peripherals because it has all the interface connections we need to wire everything up to the care system. For depth sensing, we chose the time of flight sensor because it provides really quick direct distance measurements in real time. This is important because the robot operates really close to the user's face and we need reliable proximity feedback for safety. Compared to the other simpler proximity sensors, the time of flight sensor was picked because it is less sensitive to things like the surface color and lighting condition. For the specific depth sensor, we selected the VL53L1X because it gave us a perfect balance of a longer range of measurement while providing the simple single point distance measurement that we needed. For the interface screen, we chose an LCD display because it provides all the real-time feedback that we need at a reasonable cost. And since the system only needs to show information such as like the current food selection, system state, and error messages, an LCD gives us all of that without adding any unnecessary complexity or slow refresh rate. For the specific screen that we chose, we selected mostly based on the cheapest price, the speed that it would arrive, and also making sure that it has an HDMI port to be able to connect to our system. For the user interactive switches, we chose the push buttons because they're the most simple and reliable. And since the system is for users with limited hand mobility, we needed something that would work well as foot-operated inputs, and the push buttons just made that the simplest in terms of how they are clicked. For the final choice of user input, the one we chose was the cheapest of price along with the fastest date of availability.
After comparing RGB, monochrome, and fisheye cameras, we selected the RGB camera because it provides color information, strong foot and object recognition performance while maintaining low cost and processing requirements. We then evaluated multiple RGB camera modules and selected the 8 megapixel 77-degree camera. It provides low distortion, high close range accuracy, and the best performance for the mouth detection, which is the primary vision test in our system.
For the power source, we chose a separate dedicated wall supply because the system is intended to operate continuously and reliably. Adding something like a battery would just add charging limitations and possible shutdowns when the user is trying to finish up a meal. The selected regulated power supplies also come from the manufacturers of the Jetson and the Raspberry Pi, so we can know that they provide good electrical isolation between any system components that we attach to the systems. This slide shows how the main parts of our systems are wired together. As you can see, the Jetson Aura Nano is at the center of the setup, so most of all the sensors and user controls connect back to it through either GPIO pins or its dedicated SDA and SCL for I2C communication. At the top, the Raspberry Pi 4 inside the MyCobot connects through Ethernet, and at the side, you can see the LCD screen connects through HDMI and the camera through CSI. Overall, this system is organized so we can test each part individually and connect everything back to the full system.
Now let's move on to the communication part.
For the wire communication, we use USB 0 for robotic arm control. We use I2C connect to TOF sensor and GPIO handle the foot switcher. The HDMI driven the LCD display, and we use USB connect to the camera. For the wireless communication, we choose Wi-Fi because it supports cloud connectivity, caregiver monitoring, Firebase integration, and real-time notification. Together, the interface enables reliable communication across the entire feeding system.
For the communication between all the components, the Jetson Aura Nano acts as the brain of the system. It receives the data from the cameras and sensors through CSI, I2C, and GPIO, processes that information, and then tells the MyCobot arm what to do. The mobile apps connects wirelessly through the backend server so users can monitor the system and make non-critical adjustments. And any safety critical decisions stay on the Jetson itself to keep a fast response. We will be showing our software comparisons for the app and the vision modules.
This diagram shows how the software components work together. The mobile app provides the user and caregiver interface, while the Express.js backend and Firebase handle authentication, data store, and notification. The JS Aura Nano performs vision processing and decision making, then send the command to MyCobot controller to move the robotic arm. This layer architecture keeps the system organized and makes future development easier. For the app, we create two roles, one for user and one for caregiver. The user interface is kept simple, with lock button for the meal completion and emergency stop function. The caregiver interface allows meal scheduling, monitoring, and viewing feeding history. Firebase is used for authentication, data store, and push notification. Whenever the user hits done, the caregiver automatically receives the notification, enabling remote monitoring and improved communication between user and caregiver. In this flowchart, we can see first, user can log in or create an account. After authentication, the app loads either the caregiver or user interface. Caregivers can manage meal schedule, monitor feeding section, and view meal history, while user can mark meal incomplete and access the emergency stop function. This role-based design to keep the app simple and easy to use. For this front end, we choose React Native because it supports cross-platform development, low development complexity, strong API integration, and a large development ecosystem. This allows us to build and maintain the application more efficiently while meeting all project requirements. For the backend, we choose Express.js because it provides high performance, low development complexity, and strong REST API support. It also integrates seamlessly with our React Native application and Firebase service, making it a practical solution for handling communication between the mobile app and the cloud. We also choose Firebase for database because it provides real-time data synchronization, strong integration with mobile application, and scalable cloud storage. It also supports authentication and push notification, making it well-suited for the care monitoring and the caregiver communication system. For the deployment platform, we choose Vercel because it provides scalable cloud hosting, remote access, cloud maintenance, and simple deployment. This allows the application to be accessed from everywhere, while reducing the effort required to manage the hosting infrastructure. In this project, we choose Python because it offers a strong AI and computer vision library support, excellent compatibility with the Jackson Orange Nano and Microsoft platform, and a fast development process. The advantages make it well suited for implementing the vision processing, decision making, and the robot control function required by the feeding system.
Initially, the software flow starts with the user pressing the button. For this first iteration, they press the Ready for Next Bite button, which validates whether the arm is already in default position or if there's already food on the utensil, which if there's already food, then it would continue with mouth tracking and feeding the food directly. Otherwise, it'll look to the plate to check if there's food and then scoop the food and then move on to mouth tracking. If there is food on the plate, then the arm moves towards the food to scoop the food. And then afterwards, the utensils check to make sure that the food has been obtained. If it hasn't, then it would retry the scoop. If there's any errors, it'll be displayed on the LCD. So once the food has been scooped and the utensil has been checked that it has the food, then the arm returns to default position, and then the computer vision is used to detect the mouth. And once again, if there's an error, it shows on an LCD screen, such as if there's no mouth detected or too many people detected. And the arm continually moves while the distance using the time of flight is not yet 0, and that means that it hasn't reached the mouth yet. But once it has, then it stays there for a certain delay for the user to eat the food. For the other button-initiated actions, the alternate food just increments the variable so that when the other function is getting the food, then it would use like the current selection of the food to choose which section of the plate to scoop from. and the emergency stop will send a notification to the app. And also it'll halt the robotic arm in its position for a certain amount of time. We selected the Jetson Orin because it gives the best balance of performance and practicality, because it can run the vision algorithms in real time and has a GPU acceleration. We selected Python because it has great support for AI and computer vision tools, making it easier to develop the vision system. We chose OpenCV and MediaPipe because they work well together for processing the camera images, calculating the positions, and giving reliable face and mouth detection without needing to train it. For mouth localization, we chose facial landmark detection because it gives reliable real-time tracking of the mouth position. For mouth localization, we use MediaPipe because it provides accurate facial landmarks and it's optimized for embedded platforms, and it's also a ready-to-use pipeline. We selected object detection because it can localize and classify objects at the same time. We selected the YOLO family because it offers strong accuracy with real-time performance. We chose YOLO V26 because it delivers the best overall performance when deployed on a Jetson.
We selected fiducial marker-based identification because it provides fast and reliable compartment detection without requiring AI training. It also has low computational requirements, making it well suited for our embedded system. We then decided to select AprilTags after comparing these products because they provide accurate and reliable localization while maintaining fast real-time performance. They are also well suited for robotics applications and can run efficiently on embedded platforms.
The first state of idle is when the robotic arm moves to its default resting position and remains there until a user command is received. For the state 2, where the utensil is being checked, the region of interest is defined around the utensil tip, and YOLO V26 is running its region of interest to detect food. And if there's already there, then the system skips scooping and proceeds, otherwise it continues looping until food is acquired and displays an error. For state 3 in the plate check, the AprilTag initialized coordinates are used to define localized regions of interest across the plate sections. Then YOLO checks for available food within the region, and if no food, then the system terminates. But if there is food, then it transitions to state 4, the mouth detection and feeding, where MediaPipe performs the face detection and then uses the mouth region of interest to, as well as the time of flight sensor for distance to deliver the food to the mouth, and then returning back to state 1. This diagram shows how data flows through the system from sensing to the action. The system takes two inputs, the camera module, which provides the video frames, and the distance sensor for the distance. The video stream feeds into the perception pipeline where the two models run in parallel, the MediaPipe performing high-frequency mouth tracking and the YOLO running at a lower frequency to detect food on both utensil and plate. At the same time, the distance sensor feeds into a safety module that continuously monitors and can halt the system if the arm gets too close to the user. All of the outputs are sent to the central decision and state machine block, and this determines the next action, whether it's to proceed with feeding, reverting to a previous state, or stopping for safety. Feeding system acts as a top-level controller. It maintains the current state and coordinates the state machine, perception pipeline, and safety monitor. The state machine manages progression through the 4 operational states, handling transitions and resets without being responsible for the internal logic. The states serve as an abstract base class which is inherited by all 4 concrete states. Each concrete state handles a specific function. The perception pipeline integrates the MediaPipe and YOLO and AprilTags, and the safety monitor operates independently of the perception by continuously reading the distance sensors and safe boundaries of the arm movement.
Now let's go over prototyping and testing of our system.
For hardware testing, what we did was individually connected each hardware component to the Jetson Orin Nano and made sure that it was able to be configured and was compatible with the system. And for our test setup, we took the time of flight sensor and we measured the distance accuracy by printing out what the sensor measured the distance as and then checking it with a physical ruler. And our average error for that was around 1.8 centimeters, which is enough for our use case. We also checked the RGB camera and made sure that it had continuous video capture because that is important for our mouth detection and also our plate and utensil detection. For the LCD display output, we made sure that there was real-time interface updates. So anytime we sent a new output to it, that it would change immediately so that the user has an accurate system update. For the robotic arm calibration, we used a ruler once again, and we had a bunch of different set locations, and we made sure that the robotic arm would arrive there accurately and precisely every time to make sure that when we do send the robotic arm a motion that it goes to the destination that we expect it to go to. For hardware challenges, our main problems were physical in terms of secure wiring, since both the Jetson and the robotic arm we can't solder directly on. Using things like high quality female header wires or screw clamps where possible will help alleviate that problem. There are also just a lot of space limitations since there is a lot of moving parts on this project. Things like the robotic arm moving in ways that could damage itself or hurt the user. We had to impose range limitations, and we are slowly improving that to make sure that the robot never moves in a way that could hurt itself or hurt other people.
For the software testing of the app notification, we launched it on the mobile device and configured the time for the mealtime. We observed the notification timestamp and time, and we ultimately observed that the notifications were accurate in being 15 minutes before the set time. For the YOLO classification software testing, we used the white plastic spoon and a 4-compartment plate with April tags on the side and raw oatmeal for the food. The code was launched on the Jetson, and it uses the camera feed as input and LCD to display the detection. We observed low latency and inference times between 16 and 30 milliseconds, where the average was about 23 milliseconds, which was expected. We software tested the April tags and placed one on each corner of the quadrant. In the code, we allotted 20 seconds for the camera to find the April tags, and once all 4 were found, then the coordinates were recorded for the points between the tags. And we observed that it was quick in finding the 4 April tags with low latency, and there were no lag when the 4 tags were in view. So far, we faced software testing challenges in the initial PyTorch model that wasn't converted using the Jetson inference model was really laggy in the video feed, and after we transformed it, which was the solution, it was better frame rate.
Now let's go over the budget, work distribution, progress, and our future plan. This is the current budget for our project. We have purchased all of the parts that we needed, and the total came out to be $490. To make sure that we have an efficient project development, responsibilities are divided among team members based on their areas of focus.
Currently, we're working on the optimized placement of the time of flight distance sensor, as well as translating XY coordinates from video feed into usable coordinates for the robotic arm.
This timeline shows our remaining project milestones. We have listed out all the dates of our deadline, and we will follow this plan as we move on. This is also the end of our presentation. Thank you so much for listening, and we're happy to answer any questions from you.